Assalamu alaikum wa rahmatullah. Good morning, good afternoon, and good evening. Welcome to our new lecture, Information Evaluation. And today we'll talk about resistivity and we'll go through some examples in which we will carry a quick look formation evaluation. So we have covered resistivity log in previous year in details. We have gone through the principle, the application, and some of the application and the interpretation. And today we will just highlight some of the main aspects of the tool in order to understand how we can do the interpretation of the resistivity log. As we said earlier, that resistivity tool was the first tool that have been discovered by the Schlumberger brothers, and starting from there, the new tools have been developed. Resistivity tool is basically measure the resistivity of the rock, or the resistance of the rock to the current flow, and it depends on size and shape of those material. It's reciprocal of conductivity, and since we already have only rock and fluid in the subsurface, and the fluids contain both water and hydrocarbon, so hydrocarbon rocks and fresh water will have high resistivity, while salt water will have low resistivity and high conductivity. As we said, also, if we recall the information that we have about resistivity tool, we talk about in details about the type of resistivity tools. We said that we have two types. We have the Laterolog, we have the Induction log, and we said that Induction log is more efficient in the drilling condition in which we use fresh water or oil-based mud, while Laterolog is only usable in the environment in which there is a fresh water. And we said that basically in the Laterolog, or the dual Laterolog, we have a spherical focus log, we have Laterolog shallow, and we have the Laterolog deep. So and if you remember that we said that in the borehole environment, we divided the formation near to the borehole into three zones: the flushed zones, and the embedded zone, and the in-embedded zone. And we said that the flush zone is a zone in which the drilling fluid flush all the fluid, and the only fluid remaining in that zone is the drilling fluid. The embedded zone, in which both fluids occur, the drilling fluid and the formation fluid, and it's kind of the transition zone in between, while the in-embedded zone, in which that zone in which we only find the formation fluid, which is either water or hydrocarbon. And the resistivity that is measured in the flush zone is RXO, while in the unembedded zone is RT, or the true resistivity. So starting from there, from this, that the spherical focus log is actually measure the resistivity in the flush zone, and lateral log shallow or induction log medium is measuring the resistivity in the embedded zone or transition zone, while the lateral log deep or induction log deep is measuring the resistivity in the unembedded zone. So starting from there, we can go through some examples or some scenarios and to see how those resistivity log are responding to the various fluids in the formation. So in the first scenario, we have water feeding zone with fresh water mud. So since the drilling fluid is fresh, and we said that since it's fresh, it will contain low salt, and since it contains low salt, it will be low conductivity. It will have low conductivity, and for that it will have high resistivity. So from there, we're expecting that our spherical focus log, which is the solid line, to read high resistivity, since it's read the resistivity of the fresh drilling fluid, and that is the case that we have. The solid line is reading high resistivity, and since the formation is water bearing zone, and we know that the formation water is always salt since it contains a lot of salt dissolved in it on it, so we're expecting that the induction log deep and induction log medium to read lower resistivity, since it is highly conductive. So as we see here that this is the dashed line, this one is the induction log deep, since it's reading the formation water, which is highly conductive. It will be very low resistance, it will have a very low resistance, and that's the case, while the induction log medium will have a slightly higher resistivity comparing to the induction log deep, since it's might be in transition between the fresh water and formation water. Another scenario is in which we have water bearing zone with salt water mud. So the salt water mud will have high conductivity since it contains salt, and since it have high conductivity, it will have low resistivity. So expecting that our RXO in this case to read a very low resistivity, which is the solid line. While since the formation is water bearing, and we said that it contains salt, so it will be having high conductivity and low resistivity. So the same both flush embedded and unembedded zone, or flushed and embedded and unembedded zone, all of them, they will only contain either fresh either water formation water, which is low in resistivity, and or the drilling fluid or salt water from the drilling fluid, which is also low in resistivity. So we have that the three logs will be having the same or almost the same resistivity values, and we will see that there is no separation between them. Now another scenario is that we have a hydrocarbon bearing zone and a freshwater mud. So a freshwater mud means that we are having low conductivity, so it will be high resistance, and so we're expecting that our reading in the flushed zone, which is the LL8, will be high since it's fresh water, so it will have a very high resistivity. And since the formation fluid is hydrocarbon, which is also have a high resistivity, it will also we will see that the induction log deep and induction log medium, the induction log deep in red and the induction log medium in blue dot lines will have also high resistivity. But normally the flush zone will have high resistivity than the unembedded zone. So we can see that the fresh water will have in the flush zone will have high resistivity comparing to the unembedded zone, and that's maybe due to the fact that there is always formation water, and this water, which is having some kind of conductivity, will slightly reduce the resistivity of the hydrocarbon in the unembedded zone. And in this case, in this scenario, if we check that the gamma ray log response, which is this line here, we see that along this interval that we are having a low gamma ray response, which indicate that this formation is shared. It's low. It's either share. It's sand, or limestone, or carbonate. But we can see that from the SP, it's permeable formation. So that is actually coincide with our interpretation in the resistivity tool. Now another scenario is that we are having hydrocarbon bearing zone with salt water mud. So we have hydrocarbon, so we're expecting that our unembedded zone, or Laterolog deep or Laterolog shallow, both of them will have high resistivity. And since we have salt water here, which is having high conductivity, will have low resistivity. So, and since the microspherical focus log, the green one, will read in flush zone, and in the flush zone we only have the drilling fluid, which is the salt water, which is in low resistivity, we're expecting that our microspherical focus log to have low resistivity response, as we see here, comparing to our Laterolog deep and spherical or Laterolog shallow, which is reading embedded and unembedded zone, and that zone which contain hydrocarbon, and hydrocarbon will have higher resistivity comparing to the salt water. So we can see that the LLD is reading high for the hydrocarbon, and the LLS, which is the embedded zone, it's slightly less resistivity compared to LLD, and higher resistivity comparing to the microscopic focus log. So this is how we can use our knowledge about the response of resistivity tools to guide us in order to interpret different type of formation fluid that we have in the borehole. We can differentiate the zone of that contain water and zone that contain hydrocarbon, and even using, as we said earlier, the neutron density, we can differentiate the oil zone from the gas zone based on the separation between the neutron and density. We have higher separation, that's an indication for gas, while a little less separation is indication for oil. So to summarize everything, we will go through another example in which we will do a full quick look formation evaluation through the lithology, porosity, and resistivity log. Before that, we have to understand some industry related things. We have the log header, and in the log header we have some information that we need to be aware of. So basically, any log header, it might contain this information plus and minus others, but there is always in any log header you will find the name of the logging company, the name of the logs, that is which are present in the log, geographic data, the well operator, the well name, and the well location, which is the company, the name of the well, the field, the country and the state, the well location in details, the elevation of the well. And the elevation of the well is very important because according to this elevation, any depth value is being referenced. So the reference is not actually, when we say that the total depth is for example 5,000 feet, we are not measuring this depth from the sea level or the elevation of the land in that area. It's actually measured based on the Kelly bushing. So any depth in the log is actually a reference to the Kelly bushing or the elevation reference, which is mentioned in the log header. So we have to be very careful in checking all those information before carrying any other before carrying our interpretation. Another information that we can find is the name of the engineer that was there during this logging job, the logging date, the depth intervals. And we have said that normally the logging jobs it's not carried out through the entire borehole interval. It will only be along the specific zones. So those zones have to be mentioned in the log header. We have some values of resistivity of mud, resistivity of mud filtrate, and resistivity of mud cake. All those resistivities values has to be mentioned because they are very important in calculation of water resistivity, which is used for calculation of water saturation. So, and in which temperature they are being measured. We have the borehole temperature also. We will find it in the log header. Type of drilling fluid, the density of the drilling fluid, the bed size, and if there is any remarks regarding, for example, if the well is deviated or vertical. For example, if this borehole is encountered several washouts in the upper part of the hole, so and repeated log run over bottom 300, so that means the logging has been repeated for that specific interval. Now, for the quick look formation evaluation, we have certain steps that we follow. So we always start with our lithology log in order to identify the zones which is containing reservoir rocks, and we can indicate that by either SP response or the low gamma ray response. And if we identify a zone which have low gamma ray, that means this zone is potential reservoir rock. So then we go to resistivity log, in which we will be looking for a zone that having high resistivity than shale. And why high resistivity? Because hydrocarbon resistivity is always high. So if we find the low resistivity, that means it's possibly wet because it contains formation water, and we said that the formation water is highly conductive, so it will be low in resistivity. While if we find the high resistivity zone, then we will go and check porosity. If it's low in porosity, that means it's tight. The reservoir is a tight reservoir. While if we find higher porosity, that means this zone is a zone of interest, and it possibly pay zone. So we can carry out further quantitative analysis in which we go more in details in terms of lithology type, what type of lithology that we have, the porosity values that we have, and we go for saturation computation. We have to calculate our water saturation in order to get our hydrocarbon saturation, and then we go further and calculate our reserve. This is it's just a reminder of we have talked about how we read the logs, and in that, understanding of the scale is very important. So in all logs there is no issue, since it's all in all logs we have a linear scale. So we said that we just find the minimum and maximum values and the range, and divide the range by number of intervals or blocks that we have here. So we compound the value of each interval of those, and then we can easily read. While in resistivity log, since the scale is logarithmic, so we will see the minimum and maximum value. More or less, most of the time the scale is fixed from 0.2 to 2000, and the first part is 1, so we have 0.2, 3, 4, 5, 6, 7, 8, 9, 1, and starting from here we have 1 and 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and from 10 to 100 we have 20, 30, 40, 50, 60, 70, 80, 90, 100, and so on. So based on that, we will just see in which in the depth of interest, in which line we want to, in which we want to read, and we find the line in which the curve of the log is lying, and we just directly can read the value of the resistivity from there. Now this is a summarization for the log response before we go for our example. The gamma ray log, the density, the neutron, the sonic, and the resistivity. The sandstone, we will have, of course, low gamma ray. The density will be the density of the sand, which is 2.65, and the neutron will read negative. And the interesting thing about neutron log is that since we know that it's sensitive to hydrogen, if there is hydrogen, it will read low. If there is no, it will read high porosity. If there is no hydrogen, it will read low. That's why it will read minus for porosity for the sand, since the sand is containing no hydrogen. And the other fact that it depends on the atomic mass. So if the rock is having an atomic mass less than the atomic mass of limestone, it will be negative, and if it's the rock that it's or the lithology containing the atomic mass of the rock is higher than the limestone, it will be positive. So you can do this exercise and check. You will find that the atomic mass of sandstone, which is representing SiO2, the quartz, will have an atomic mass less than the atomic mass of limestone, which is CaCO3. So that's why it will read -4. While if we check dolomite, which is CaMgCO3, will have a higher atomic mass comparing to the limestone, so that it will have higher positive, more than 0 or above 0. The acoustic log, it will have different values for different lithologies. Resistivity as well, we have described the response of resistivity previously, depending on the resistance of the it's more or less related to the resistance of the fluid in the formation. Since more or less all the formation are having high resistivity, only anhydrite salt will have an extremely high resistivity. Only shale will have low resistivity since it contains water on it, and that's even the formula of the clay minerals contain OH or water on it, so that's why it will have low resistivity comparing to any other material in the formation. And now this is our example that we want to go through it. We'll go step by step to carry out a quick look evaluation for those log in this example. So as we said, that the first thing that we go through is the lithology in order to identify the reservoir zone, and in this we are depending on the gamma ray log, and we know that the zones which contain high gamma ray are actually shale, while the sand will be represented by the zone which is containing low gamma ray. We have the depth track in here, which is representing the depth, so we can see clearly from this example that this zone is a shale zone, which is not a zone of interest, while this zone can represent a zone of interest, and those small sand layers. Now we go to the resistivity. We saw here that this is the value here is around 1, and this is shale resistivity, it's very low resistivity, while we can see a sudden increase in the resistivity values reaching up to 20, a value of 20, and that's the high resistivity comparing to the shale resistivity. And as we said when we were talking about resistivity, that hydrocarbon will always have high resistivity. Tight streams, which is having low porosity, will also have high resistivity values. It contains no water or no fluid on it, so it will have high resistivity. Low deep resistivity means either shale or wet sand. If the sand is wet, it contains water is conductive, we have low resistivity, or the shale also contain water, the water is conductive, so it will have low resistivity. If we have separation, or if you remember in resistivity log, we talk about the invasion process, which is the movement of the drill fluid into the formation. And that's, if we have a separation between the resistivity curves, that's mean that the formation is permeable, and there is a fluid, there is different fluid in the formation. So we have a drill fluid, we have hydrocarbon or water, or either that the formation is permeable, allowing the drilling fluid to invade or to move from the borehole inside the formation. Now the track 4, which is the porosity track, and we talked in details about the response of the neutron and density, and how we can use the neutron and density crossovers to interpret or to identify the different lithology. So if you remember that we are having, if we have neutron to the left and density to the right, that's mean our lithology is shell, while if we have the density to the left, neutron to the right, that's mean our lithology is sand. We also said that then if we have neutron to the left, density to the right, is also for dolomite, and the way that we differentiate between dolomite and neutron and shell is using the gamma ray. So in this case we can see that this zone is a zone that is containing sand, and to differentiate if it's sand or that contains sand, and to differentiate if this zone is containing oil or sand or gas, we can know that if it's contain oil from the resistivity, as we saw in the previous, if it have high resistivity, that means it's either hydrocarbon or it's either oil or gas. And if the separation between the neutron and density is large, that means it contains gas, while it's low, where it's narrow, it means that it contains oil. And if they are overlaying each other, that means it's water bearing zone. Now to summarize all the steps, the first thing we go gamma ray. If it's going to the left, if yes, if there is a potential hydrocarbon, does the resistivity goes right, which is mean if we have high resistivity values. Now if this is the porosity greater than 0, that's mean do we have porous formation. To identify permeability, we go for SP log. The deflection is the SP log is to the right. The SP log, to identify if it's to the right and to the left, it depends on the salinity of the drilling fluid comparing to the formation fluid. So we have to put this information in our mind before interpreting the SP log. We cannot generalize that if it's to the left it means it's permeable, if it's to the right it's so we have to consider the salinities of both the drilling fluid and the formation fluid. Now let's put it all together. Sand zones, according to the gamma ray, we identify those two reservoirs. From the resistivity, we identify the zones of hydrocarbon. We have this shale. So any zone above shale is a zone of interest. So we have high resistivity in here, we have another high resistivity in here. Now we go to the porosity and we say that we saw that the porosity of sand is more than 30% in this zone, and according to the separation between the neutron and density, you identifying that this is a gas zone, while this is smaller separation compared to this one, and even the resistivity in this one is less, in this one is higher compared to this one. So this is our oil zone, while this is our water zone in which the neutron and density are coinciding with each other or ever overlaying each other. Now another example is this one. We have this zone in which two reservoirs, in which this one is low gamma ray, another one which is having a low gamma ray. Now we come to the resistivity, identify the zones of hydrocarbons. We find this zone, and now we come to the porosity. We have porosity more than 30% in this zone, and the separation between the neutron and density is very high, so we can identify this zone as a gas zone, while this zone, which is having very low resistivity, less than the shell, and the neutron and density are overlaying each other, or that means it's a water zone. Another example from Brunei is in which we have two reservoirs, this one and this one, and we can see here that there is no, and that the resistivity value is less than the shell resistivity, which is indicating that this zone is the water zone, and we are having a slightly higher resistivity in this zone, which indicate that this zone is containing hydrocarbon. Now, since we don't have a very large separation between the neutron and density, we can see that the density is to the left, neutron to the right in most areas, like this zone, and this zone, while the separation is not so large, so this zone containing oil, while this zone is definitely water bearing zone. Something important as well is the neutron density crossover, and this is a correlation between, in which we can relate our understanding to the neutron and density log response in different lithologies, and using and how they use this response in order to identify different type of lithologies. As we said that since the neutron and density are calibrated into limestone, and we are actually measuring the porosity in limestone scale. So if the formation is limestone, we assume we said that the both line will be overlaying each other, and we will get the exact porosity value, which is 20. This is 20% water limestone, so it will give us the exact porosity value. And if we plot the value of the neutron and density, we have the bulk density, we have the neutron density. If we draw a line from this value and this value, it will intersect in the point, and this point of intersection, we can get the value of the porosity and the lithology as well. So if in this case we are having 20% density porosity and 20% neutron porosity, so this is our 20% density porosity, and this is our 20% neutron porosity. The intersection is this point, this point is 20% limestone. So we know that this formation is limestone with a 20% porosity. For example, in this one we are having limestone with porosity is more than 20% in this case, so it's around 25 for density, porosity, and we have around also 25 neutron porosity. So the intersection is somewhere here, and that is give us a 25% limestone. It's not 20%, it's 25% water limestone. So you can check this for different let us check. This is the dolomite. We have around 25% neutron. So we have 25 neutron somewhere here, and we have around this is 20 and this is 10, so it's around 15 density. So this is around 15, so the intersection is somewhere here, and that lays in dolomite, so we can know that this zone is in the 20% porosity dolomite formation. So this is how we can use the neutron density cross plot to identify the lithology and the porosity values as well. Now as water saturation, we will stop here and we will continue talking about the water saturation calculation and the reserve estimation in the next lecture.